Hello everyone. It is my great honor to have this chance to share our recent research. My name is Chen Wang, a PhD student of Southeast University from China. My talk is about performance evolution of liquid air energy storage with air purification from molecular simulation to mathematical modeling. My talk is divided into 4 parts: background, system description, results and discussion, conclusions. First is the background. As all we know, renewable energy is becoming more and more important and popular nowadays. The left picture shows the top 20 countries by the size of their targeted non-hydro renewable power additions between 2020 and 2030. Many countries have set targets and tried their best to add more renewables for combating climate change. The right picture shows the increasing renewable shortfall for the RE100 from 2018 to 2030. The future must belong to renewables. But as most renewables are intermittent, how can we deal with the supply and demand issue of renewables? Energy storage technologies can be the answer. There are many types of energy storage technology for different applications at different scales. And as a promising solution for grid-scale storage technology, liquid air energy storage has attracted extensive attention over the years due to several advantages. The right picture shows the concept of the baseline areas. However, most traditional LOS studies ignore power consumption of H2O and CO2 removal. Actually, removing H2O and CO2 is important in cryogenic cycles. But mostly, it is assumed that inlet air is purified, resulting in overestimated round-trip efficiency. It is also unknown how the air purification removes impurities and regenerate fuel time later. There is no mathematical modeling of air purification in LOS now. This is the first LOS pilot plant in the world. I took this photo last year at the University of Birmingham. Actually, the pilot has air purification unit which is marked by the red circle, although it is hard to see the body of the air purification unit from the picture. This page shows the flow diagram of the proposed LOS system, which consists of a charging cycle and a discharging cycle with a regeneration step of the adsorber beds. At off-peak times, the charging cycle is powered to produce liquid air by excess electricity. H2O and CO2 in the ambient air can be removed in the adsorber beds. At peak times, the discharging cycle works to generate electricity, and the air exhausted from the discharging cycle goes through a heater to heat adsorber beds, and then goes through a cooler to cool adsorber beds for regeneration. This study focuses on the H2O and CO2 removal in the adsorber beds. The characteristics of H2O adsorption on activated aluminum can be obtained easily from some research papers, which shows activated aluminum has good ability of H2O adsorption in the air. But it is difficult to find the characteristics of CO2 adsorption on zeolite 13X APG at a specific state in the air purification process. The analysis of CO2 adsorption is crucial to this work. Monte Carlo simulations of CO2 adsorption are therefore carried out in order to verify feasibility and advantages of removing CO2 by the zeolite 13X APG. We reconstructed the zeolite 13X APG modified on a FAU structure. The left figure shows a final snapshot of the modified zeolite 13X APG. When applied pressure increases from 0 to 100 kilopascal at the working temperature, the adsorption loading of CO2 is much higher than that of nitrogen, oxygen, and argon. It reveals that zeolite 13X APG has a reverse selectivity of CO2 adsorption compared with other components. With applied the working pressure, the adsorption loading of CO2 decreases greatly at the temperature is between 295 Kelvin and 323 Kelvin, whereas the adsorption loadings of nitrogen, oxygen, and argon decreases slightly at other temperature. When the temperature is around 443 Kelvin, the loading ratio of CO2 is nearly zero. This makes sure the theoretic foundation of heating the adsorber for regeneration. We established a mathematical model of the adsorption step in order to describe the intrinsic adsorption mechanism and verify the rationality of the adsorption process. Through simulation, we got two description pictures. One is the breaking through curves of the adsorption bed for H2O and CO2 removal. The breakthrough point occurs at about 4 hours. The other is the concentration different distribution of H2O and CO2 in adsorber beds. As time goes on, the mass transfer rooms of H2O and CO2 both move up until adsorber bed reaches adsorption saturation. The left table lists some simulation parameters. The right table shows some important simulation results. Round-trip efficiency and exogen efficiency are employed as two key parameter indexes. The charging pressure in the charging cycle affects the performance of the proposed LOS. From the left figure, an increase of the charging pressure leads to a significant increase in the liquid air. What's more, a higher charging pressure is also beneficial to the exogen efficiency of the charging pressure. The right figure indicates that the proposed LOS has a lower round-trip efficiency compared with the baseline LOS. This is merely due to the energy consumption by the regeneration step of adsorber beds. As the charging pressure increases, the round-trip efficiency of the LOS system with air purification increases, which is around 5% lower than that of the baseline LOS system. In this page, the left figure shows the power output of the discharging cycle increases first with the increasing discharging pressure, reaches a peak at around 12 megapascal. This is mainly due to a combination of the increasing output power per unit mass flow rate and decreasing liquid yield. From the right picture, it can be seen that the round-trip efficiencies of the proposed LOS and the baseline LOS both increase first with the increasing discharging pressure, and also peak at around 12 megapascal. Compared with the discharging pressure, the charging pressure has a more significant effect on the round-trip efficiency of LOS system. Here are our main conclusions. First, Monte Carlo simulations of CO2 absorption are carried out to show the Zeolite 13X APG is more selective to CO2 in the feed air. Secondly, a heating step at high temperature of 443 Kelvin is a necessary and effective way to regenerate the adsorber. Thirdly, the results show that the round-trip efficiency of the proposed LOS system with air purification is around 0.45 and the extraction efficiency is around 0.58. Then, compared with the discharging pressure, the charging pressure has a more significant effect on the round-trip efficiency of LOS systems. Finally, this work indicates that the round-trip efficiency of the current LOS system is overrated by around 5%. That's all my talk. Thank you for your listening. Thanks to MITAB.